Okay, we are back. We're going to do one of these uh, problems with a twist. Uh, this is a trinomial polynomial and somebody a teacher on the internet called this taking the square root method, taking the square root method, which I do not agree. I do not agree at all, because this is not a method. This is an algebra thing, and it's part of almost every single method that I've done here. It's not a method, so I do not agree. A method is like factoring or finding the what you call it, finding the intercept, or finding the perfect square, finding the vertex form. Those are method. This is not a method. I do not consider that to be a method. In any case, this is a polynomial which should be written like this. And I'm putting the exponents. Sometimes, exponents are not shown when it's 1, and the x is not showing when the x is to the 0 power. An x to the 0 power just is equal to 1. And obviously this is the x raised to the first power. All polynomials follow the same rules. So it always start with x0, then x1 to the first power, then x to the second power, and x to the third power, and it just goes on and on and on and on. Yeah? So that's why this is called a trinomial, because there is 3 x's. Yeah? Okay, so I wanted to clarify that. Now, the first thing we do with this problem is I'll rewrite it the way I like it. Because I don't like terms on the other side. I always like to work on the problems from one side. And so you can identify that this is a trinomial where the x to the first power is 0. And so problems like this are peculiar because when you look at the graphic, you can see something special. You can see something special on the graphics. Okay, so first thing, we eliminate this. So to eliminate the leading factor coefficient, we multiply everything by 4/9/4. You see, I included the 0 because we have to multiply everything, not just what we like or what we decide we're going to show and the rest we don't need to show. It's not fair for somebody that is starting to understand this thing, and then maybe in the future they find a number on the other side, and then they don't multiply because they think that the multiplication stops on one side of the equation, and that is not true. You multiply 9/4 times everything in order to maintain the integrity of the equation. If you don't multiply the 0, you're not following the rules, even though that it still does not change anything. But in case that there is a component on the other side, then it makes a big difference. Then you will get, for sure, an error. Okay? So, then the results for that will be correct. X squared minus 12 times 9/4 equals 0 times 9/4. Okay, so now we move to the next step. This becomes 3 times 9, and this stays at 0. This right here looks like the vertex form of the trinomial polynomial. Okay, so if we rewrite this as a vertex form, which is y equal to 8 x minus h parentheses square plus k, where I don't know what symbol to use for where, but we don't put anything. Where a is equal to 1, well, in this case, in our case, a is equal to 1, h is basically equal to 0, and k is equal to 3 times 9. And sometimes I don't like to use the point, even though that this is very typical when you do algebra. So I use this just to make sure that nobody confuse this for a comma or a point or something, because like in the US they use comma to separate decimal numbers, but in other countries they use the dot. So this is very evident that we are multiplying 3 times 9. Okay, so so we do that. Well, I'm not going to multiply it because I like to leave it like that. But I'm going to move it to the other side of the equation, and it stays 3 times 9. Then we get rid of this 2 here by squaring and squaring, and that implies that x is equal to plus or minus the square root of 3 times 9, which is equal to 3 times the square root of 3, plus or minus. Yeah? So, from the equation, from this equation, if we replace the points that we have, we will have y equal to parentheses x minus 0 squared minus, in this case, we're gonna multiply 3 times 9 equal to 0. So we can visualize what we have. So if we're going to, now we can move to our drawing, our graph. This is the x coordinates, this is the y coordinates. The arrows point to the positive direction, and this one also points to the positive direction. Obviously, on that side, that is the negative direction, or downwards is the negative direction. When you calculate this in the handy-dandy calculator, you get 5.2 approximately. So we're gonna try to put it in there, but I made this thing a little bit too short. 1, 2, 3, 4, 5. Okay, so it's just fine. And we're gonna put it right on the 5 button, but it's just a little bit bigger. I know that in this problem, you see, you can see it there that h is equal to 0. This means that the axis of symmetry is lying right on top of the y-axis, and the extrema, or the vertex, is somewhere. It's on K, but right on top of the y-axis, at a point that in this case is 3 times 9, but it's negative. Okay? And I should have said that here as an error. Okay? These are the roots. The roots of the function. Yeah, okay. So now we go 1, 2, 3, 4, 5. Same thing as here, it's a little bit bigger than 5, but that's the point. The other point will be at y minus 27. We'll go on intervals of 2, 2, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 y 28. So the point is here at minus 27. So our parabola will be something like this. Remember, the parabola is symmetric with respect to the axis of symmetry. So this distance is the same as this distance. This distance is the same as that distance. So basically, when you find a point on the parabola, you're automatically finding this point as well, because all you have to do is move from the axis of symmetry the same units you move to this side, you move to the other side. Good? Okay. So, yes. Okay. Okay. So, since this is a very short video, we're gonna play with this function here a little bit. We'll clean it up, and we're gonna plot using the calculator. We already plotted. You know, I always use the calculator to double check or to carry out calculations fast, to show particular things about the parabola. And in this case, clean this up. The first number is 1. Change keyboards. 1. The second one is 0. And the third one is 27 negative. So this point should be somewhere about 5.2 positive. Let's see if it's true. Well, it shows it but we can change it to, see, it says minus 5.2 for me. And the next one, again, is 3.3 times square root of 3, which is also 5.2, but on the negative side. So it's minus 5.2. And this one is 5.2. And this is the vertex, which is also called an extrema, made of x and y coordinates. In our case, it would be 0, comma, minus 27. Okay. So the next information that the calculator is going to tell us is what h is and what k is. Okay, so x is 0. I don't know if you can see it. I'll do a close-up, because we're gonna see a little bit more information on the calculator. The next coordinate should be minus 27. There it is. Then we look at the graph, and there it is. And we can make it a little bit bigger so that until we see the point 26, which is right in the center, which means it's 27. And for the roots, you can squeeze this back. And we can actually show those roots, and also show the streamer. So the streamer is at 0, comma, minus 27, and you can see the roots. Okay, so one thing I want to do is want to play with this number. You know, like what happens if we make h big? Which I thought that the the curve should move to the left and to the right. I'm still trying to do that, but in order to do that, you could do that if x, the term x was still there, it could work. I think we can do some examples if I have time. I don't know if I have time. I want to keep this video at about half hour. It's 20 minutes now. So very quickly, so if I clean this up and I make the coordinates, I change the 0, the h being 0, I will change it to 10, just to x0, wait a minute, not, and 1 is still 1, and okay, I see why it's not changing. I see why it's not changing. So the point that I'm trying to make is not gonna work. It's because I wanted to shift this to the right or to the left. I think that the only way to do that is by adding the x term. So let's see what happens. So we use 1, and then we'll bring this to a 1, and this will be 27 minus, just to see what happens to the graph. So see, it only moves the graph upwards. It did not shift. Well, shift a little bit. You shift a little bit, but okay, but now let's change. Oh, that's a problem that's missing here. Wait a minute, maybe we still have a problem here. I did not put the you see, it did shift. It did shift, and then let's see what the roots is. You can see the roots are shifting. The streamer also move a little bit. You can see the streamer is a little bit different. So we are moving it. So let's exaggerate it a little bit more. But it's because we added this thing. If we didn't, we will be changing the whole curve, I think. let's play with it a little bit. Let's pretend that that this is still 1, and then the second one. No. Let me go back. Let's pretend that it's a 10. We'll keep the second one as 0, and the last one at minus 27. And then we say graph it, and look what happens. This is, did I do that right? You see, I did it again. I have to punch the equal sign before. Yeah. Now we can see that we're squeezing the parabola. So I wonder if how can we widen the parabola, and if we went high on the x factor, on the leading coefficient, if we make it small, Then we clean it up and we'll make it point 0.005, let's say. And then we say enter. And then we say 0. And this is a 27 minus equals. And we go graph it. Woo! Woo! Wow! Look at how much it got. Ooh! Look at it, you know, now the roots. You can see that let's see what it says. It doesn't tell me. Oh yeah, it's showing the roots. I want to see the streamer. So the streamer is not moving, which is pretty good. The streamer is not moving. But obviously our roots changed. So as we make the leading coefficient, as we make it smaller, the parabola gets wider and wider. There will be a time where the parabola will be almost aligned. Let's test that. So we clean this up and we will make it much smaller, 0.000000001. Enter. Then this will leave it 0, and this will leave it at minus 27. Enter, and we graph it. You see, it looks like a line almost. But you see, I will have to make it whoa, look how this streamer, no, not this, the roots, is like one. When I use the computer, the screen. Yeah, it's 1,643,167.67 big. See? So this parabola I had is almost a flat line, but obviously it's not. But it's extremely wide. So we can now see what happens with a trinomial when we increase the leading factor coefficient. Now, let's say that we clear this up. We put the a as 1, and we're going to play with the x to the first power. And we're going to make that 5. And we're going to keep this at 27 negative. We go enter and graph it. Boom. What the hell happened now? It disappeared. I don't believe that. It just disappeared. Where did it go? Hello? Where are you? It's gone. Wow, what the hell happened with this calculator now? So, wow, I don't know what happened to, well, let's make this a little bit smaller then. Let's make it a 1. No. Make it a 1 equals. And that one stays the same. Then now we're getting some roots. Graph, still gone. What the hell? What's the root? In Oh wow, 5 million. Is that a million? I don't know if that's how to say decimals. I still don't know what the calculator is using for decimal. It can be changed, obviously, but I'm not so sure if that's a comma separating the integer from the decimal points, or decimal points. So what about the next again? And you can see that the extreme had changed. Graphic, I see nothing. I don't know why that's happening. In any case, that's so much for this. I thank you for watching this video. I hope you liked it. Please leave a comment, leave me a like, subscribe to my channel, and I will see you next time on the next video. Take care. Ciao.